Welcome, this is MIE 519 final presentation. In our group 3, we'll discuss the automotive body frame materials and manufacturing processes. Today, steel is a primary material used in car manufacturing. Weight of a vehicle vary by size, so to take an average, around 900 kilograms of steel is used per vehicle. Around 34% of the steel structure is utilized for car body parts, which consists of body structure, panels, doors, and truck closures, etc. Steel sheets are cheap and provide resistance to denting and deformation, which is the reason why they are often used for external body parts. Steel sheets are also high in stiffness property. Vehicle bodies that include external frame, doors, etc., are typically manufactured through a process known as stamping. In the automotive industry, stamping is a forming process to shape raw materials. External force is put onto the plate of a metal and pressed to form a workpiece having a desired shape that is obtained. By this method, both steel and aluminum parts can be formed. Through one experimental model based on the cumulative carbon emissions generated from the stamping process has shown that the largest contributor, roughly 91%, is the raw material acquisition process, as known as steel mining. Now, this means that steel extraction contributes to most of the carbon emissions generated about the stamping processes. Therefore, a different approach to forming is needed to reduce emissions and to also produce materials with even better material properties. Also, for a new material like carbon fiber, which go outside of the scope of metallic materials, stamping may not be applicable and require modifications. Vehicle weight reduction has been the main focus of research in the automotive industry. While reducing weight is one of our criteria, it is important that the overall material properties of the car body parts do not compensate for the reduction of weight. It must be strong in material properties and lightweight, and importantly, reduce carbon emissions in between stages of production processes, as well as the material itself. By continuing with 3 objectives, which are weight reduction, lowering GHG emissions in process and material, and to enhance material properties, replacing steel with carbon fiber is our way to continue with this project.
To echo on the problem at hand, the need in the automotive industry has been identified to be strong, lightweight, and intricately shaped parts manufacturing. An example is aerodynamic fenders. Currently, high-strength steel and baked mild steel are used to make these parts in a process called hot stamping. As the name suggests, steel sheets are heated at 700 degrees Celsius or more and pressed into a die. Then it is rapidly cooled to harden on the mold shape. The heating process, namely austenitizing, forces steel atoms to take a face-centered cubic structure in the lattice. This allows for ductility and uniformity of thickness around corners. The cooling process, or quenching, brings this steel to a brittle state where plastic deformation is allowed. The deformation tangles up non-crystal dislocations from the austenite state, making the part fracture-proof. The result is high-strength steel part. As an innovative approach, we found fused filament fabrication, or simply 3D printing of carbon fiber, to be fitting. The composite has nylon-based matrix and 2 choices of fibers, continuous or short. Continuous fiber is strong but difficult to bend, and the printers are closed architecture due to being state-of-the-art. The second choice of fiber is short fiber. Short fibers are small carbon filaments that can easily position itself around corners. The process of printing with these filaments is similar to polymer-based printing, where the composite is heated and extruded on a plate. Printers for short fibers are simple. However, short fiber printed parts are not as strong as continuous fiber. The carbon content is lesser, and adding more carbon makes weaker interface between filament and matrix, resulting in creation of voids. These voids affect quality. So which choice of fiber is the best? The answer is short fiber. Short fiber printing is better than stamping process as well, because unlike some 30 different grades of steel which are difficult to make, short fiber only requires variable density of filaments. Also, in stamping process, elastic springback effect upon offloading pressure is a major factor for distortion in shape. Short fiber printing has no such issue, and it does not require trimming or polishing. Overall, the new approach meets design criteria of being lightweight. It can make features in hollow, saving materials. This process is particularly appropriate for aerodynamic parts such as hoods, fenders, and spoilers.
On average, 900 kilograms of steel is used to manufacture various automotive body parts. Switching from steel to carbon fiber reduces vehicle weight by 720 kilograms. A study concludes that for every 57 kilograms of weight reduction, there is an increase of 0.15 km per liter of fuel mileage. For our analysis, 720 kg reduction results in 1.89 km per liter of fuel increase in mileage. For our 200,000 km of travel, the estimated fuel cost savings is around 104 Canadian dollars per 10 kg of weight reduction. This data is based on a fuel price of 1.3 Canadian dollars per liter. 720 kg weight reduction translates to 7,488 Canadian dollars worth of fuel savings. Moving on to the environmental analysis, in European Union, current climate targets require 60% reduction in transport emission by 2050. According to European Commission's 100 kilograms of weight reduction reduces CO2 emissions by 7.6 grams per kilometer. So a 720 kilogram weight reduction from replacing steel with carbon fiber results in approximately 54.72 grams per kilometer reduction of CO2 emissions. With regards to the societal impact of weight reduction, the safety of a vehicle does not actually depend on its weight but rather depends on its footprint, which is the area between the four wheels. Lightweight vehicles can still be safe if they have footprints within the safety standard and made of high energy absorption materials. Under an impact, carbon fiber has 4 to 5 times higher energy absorption per kilogram than steel and aluminum. High energy absorption leads to reduced impact time and consequently minimize injuries to the passengers. Despite its advantages of weight reduction, carbon fiber is still relatively expensive in comparison to other metals. Unlike steel, it cannot be easily repaired once the fibers are broken under a significant compressive load.
Continuing with our technical analysis, we'll be looking at the manufacturing process itself. So our proposed solution is 3D printing carbon fiber. But due to this being an extremely experimental process, we'll be comparing it to conventional processes such as injection molding or autoclave molding. So first looking at our energy requirements. For 50% CFRP composite, it requires over 1100 megajoules per kilogram, which is 10 times more than the energy requirement for steel. We expect this to improve significantly in the future though, with projected savings by the year 2050. Although in the case of 3D printing, we will need to evaluate certain conditions such as the energy required to heat a build plate or to operate the machine itself. So another way to evaluate the effectiveness of products is to look for savings through mileage. So currently steel is still superior to carbon fiber in this sense, or even aluminum for reasonable distances. Although there are solutions. The first one is to use recycled carbon fiber, which has a fraction of the global warming potential for virgin carbon fiber, or using lignin-based carbon fiber, which requires less energy overall but produces approximately 22% less GHG emissions. So continuing with our economic analysis, we'll be looking at a steel fender. So tooling costs are low at high volumes, but in this case are very high at low volumes, which is indicative of a high capex cost with low material costs. Inversely, carbon fiber manufacturing has a low initial cost, but material costs are extremely high. Therefore, production at high volumes is difficult. When looking at the initial investment, conventional methods such as compression or autoclave molding are competitive with steel, but injection in this case is shown not to be as advantageous as it possesses higher costs for a lower volume of production. Therefore, the specific method used plays a huge part in its financial viability. 3D printing has an initial cost at a fraction of the other methods, but has high material costs, similar to that of carbon fiber manufacturing in general. The possibility certainly does exist for mass production one day using this method though. Finally, our proposed solution using carbon fiber allows us to obtain strong material properties, produce lower GHG emissions through use, and have a lighter weight structure. Through 3D printing, we're able to start production at enormous savings, while even obtaining a higher dimensional accuracy. Although we still need to overcome the hurdles of the high cost of carbon fiber itself and make the manufacturing process more sustainable. There is a shining light though. With developments in using lignin or recycled carbon fiber, both the use and manufacturing of carbon fiber could become more economically and environmentally beneficial than steel.